Hey everybody, we're going to take a look at 1.9, the notes, and work through these problems. There's not tons of them, but it is an important cap to the chapter. So chapter 1, if you remember, took us through some specific strategies for analytic solution methods for differential equations, and then we looked at some qualitative analysis, and then we also did some numerical using the computer, Euler's method, slope fields, things like that. So 1.9 is the last of the analytic methods that we're going to learn. It's an algebraic method, and so this integrating factors method is an algorithmic method. And so what we mean by algorithmic method is literally it's an algorithm. It's a pattern that we're going to follow to kind of make sense of this. And so what we're going to do is practice, learn how to do this integrating factors method. So we're starting with a kind of familiar territory, a differential equation. You'll notice that it's a differential equation in terms of y as our dependent variable and t is our independent variable. And so what we're going to do, the first thing we're going to do is we're going to rewrite. And you'll note that I'm making some notes off to the side of what I'm doing. So my first step is I'm going to rewrite it, and I'm going to move all of my y terms to the other side. And so very similar to what we've done in the past with the lucky guess method. We write all dependent variables on the left. All the dependent variable terms on the left. And so the next thing that we're going to do is we're going to multiply through by a factor. And I put this in quotes here. We're going to talk about what that means in a minute, but we're going to multiply through by some interesting factor. And just for giggles, I'm going to choose the factor of e to the 2t power. And so I'm going to multiply my entire equation by this. Oops, plus 2y equals e to the t. And so when I do that multiplication, I wind up with e to the 2t times dy dt plus e to the 2t times 2y. And the other side, I'm also multiplying it through. I wind up with e to the 3t. Now, the action that we're really interested in is what's happening on the left-hand side. And so what we need to do is kind of pay attention to what we wound up with, or what we're getting on the left-hand side. And so these two terms right here, there's two terms, each of them have two factors. And if you kind of look closely at them and you say, e to the 2t appears in both of them. And then we've got this dy dt business going on here. So what we wind up with is, this is the result of what we're remember from our Calc 1 class as the product rule. And so this right here is actually the result of the product rule on. And so we're going to rewrite this, the left-hand side, as the derivative with respect to t. Whoops, I've got to scoop my paper up. Sorry, I'm getting used to using this video machine here. The derivative with respect to t of e to the 2t times y. The other side just hanging out. It's still e to the 3t. So I'm going to just hit pause for a second, and I want you to kind of convince yourself that what I'm doing right here is the same thing as what I've written up above, the underlined in orange. So hit pause for a second and convince yourself of that. The interesting thing here is that if you work backwards, you can see if I take the derivative of this using the product rule, I take the derivative of this and get 2e to the 2t times y, that's this term right here, plus the second term would be the first times the derivative of the second, so e to the 2t times dy dt, which is this term right here. So we're actually seeing the result of that product rule. So by choosing the particular factor, and so what I called the mystery factor here, this guy right here, this factor, by choosing the particular factor there, the question, of course, is where did that come from? But that particular factor is what I needed to multiply through to wind up with an expression on the left-hand side that can be summarized using the product rule. Now let's proceed and pretend like we already knew this was going to happen and try to solve the problem from here. So what we're going to do at this step is integrate both sides. And we're going to integrate both sides with respect, oops, got to scoot up again, with respect to t. And so when I do that, I wind up with the integral, we're going to do indefinite integral of the derivative of, with respect to time, of e to the 2t times y dt. And on the other side here, we have the integral with respect to time of e to the 3t. Now, the right-hand side is pretty straightforward. That's really just going to be an integration that we can solve, we can evaluate. The left-hand side is a little bit thornier, and we need to use an old buddy of ours, that chain rule process. And if we do it right, you can see that we've got a dt kind of up top and a dt on the bottom. Really, the argument that I'm going to make for you guys is what it's saying is integrate the derivative of this thing. And you guys know enough Calc 1 to know that when you integrate the derivative, you just wind up undoing the operation. So you kind of wind up exactly where you started. In a way, it's kind of like we're canceling those two things out. And in the process, we wind up kind of canceling the integration. And so what we really have on the left-hand side is, turns out, with a little bit of manipulation, it's the integral of e to the 2t y dy. I should say e to the 2t dy, right? Sorry, I have to cough for a second. Sorry about that, and I'm back. What we're really doing is we're integrating on the left-hand side with respect to y. That's what's kind of manipulated. The right-hand side, we're going to be integrating this e to the 3t with respect to t. And so on the left-hand side, we wind up with e to the 2t y plus some constant of integration. And on the right-hand side, we wind up with 1/3 e to the 3t plus some other constant of integration. And again, we're just kind of labeling the C1 and the C2 and keeping those straight for bookkeeping purposes. And so the very last step in this process, it's sort of straightforward. The thing that we're trying to get, if you remember the very beginning of this problem, we're trying to solve this differential equation right here. And the solution for that is going to be y equals. And so the good news is now we have the ability to solve for y, and there's no other differentials involved. So we can just manipulate this thing and solve for y. So we're going to add our next step, which is solve for y equals something. And so the very last step for us is going to be to manipulate this thing. And I'm going to kind of crunch my constants together. And so that means I'm going to have e to the 2t times y equals 1/3 e to the 3t plus some constant 3, where C3 is equal to C2 minus C1. I'm just keeping track of my constants just in case there's any concern or question later on. And last but not least, I'm going to manipulate by dividing by e to the 2t, or you can think of it as multiplying by e to the negative 2t. And I wind up with 1/3 e to the t plus a constant times e to the negative 2t. And it turns out that what we've just done is we've found our general solution. That right here is the general solution for the differential equation. And this method all hinges on that super important question back here in this step. Where the heck did that come from? Where did that e to the 2t come from? And this thing is what we're going to call the integrating factor. And this entire method that we're going to develop is called the integrating factor method. And it really hinges on where did that integrating factor come from? Because if you knew to multiply by e to the 2t, then the rest of the problem kind of simplifies in a really nice way, because you wind up taking the integral of a derivative, which really sort of undoes itself, and you just wind up with e to the 2ty, which is exactly what was inside there. So we're going to take a look at another problem. You'll notice there's a little note at the bottom that says we could use maple, and we can use maple to solve this problem. And I will post the notes that kind of go along with this using maple. I just can't do maple at the same time as I'm doing the video for this particular section. Okay, so I'm going to hit pause real quick, and then we're going to take a look at the next page. Okay, so we're going to finish up this particular video by taking a look at the next page, which is all about the integrating factor. What are the steps involved? So you'll notice there are 5 steps that we kind of went over on the last page. The first one is we're going to rewrite it in standard form, so that, notice, all of the terms, the y terms, are on the left, and the only thing that's on the right would be some function of the independent variable. Step 2 is all about computing this integrating factor, and we're going to get into this right here, which is our recipe for finding the integrating factor. The integrating factor is this guy right here, mu, and you can see that mu of t, it's a function of t, always a function of t, not a function of y at all. And all we do is we take e raised to a power that is the integral of g. The g coming from that multiplier, that thing that's multiplying by y in our linear differential equation. And that right there appears in our integrand right there. And so we're going to integrate. But you'll notice for various bookkeeping reasons, we're just ignoring the constant that would come out of this integral up here, up top. It turns out you don't have to ignore it. It'll just fall out in the process. It'll get absorbed into another constant later. So we're just going to ignore it here. And then in step 3, remember, we multiplied both sides, multiply by the integrating factor. Step 4, we confirm that the left-hand side is the result of the product rule. So if you did it right, it always works. That it's the result of the product rule for differentiation. And then last but not least, integrate and then solve. So you integrate and then you solve to find that general solution. So down on the bottom, just a quick practice. You'll see there's 2 things that we can practice with. So in the first case, our independent variable is t, our dependent variable is y, and so we're going to move all of our y terms to the other side. Now, I can't really separate. This isn't a separation of variables. I'm going to move this to the other side because it's a term involving y. So I'm going to rewrite this. This will be my step 1, to rewrite dy dt plus, I'm going to write it like this, 1 over t times y equals 2. And the reason that I did that is so that I can quickly identify this thing right here. That's my g of t. That's the function of t that is the multiplier of y in my linear differential equation. And once I know what g of t is, then I can figure out what my integrating factor is. So that means mu of t is going to be my integrating factor. And that's equal to e to the integral g of t dt. Or in this case, e to the integral 1 over t dt. Now, I'm not worried about the e right off the bat. So all I need to do is figure out what is that integral equal. And it's really just e to the power natural log absolute value of t. And again, we ignore the constant due to integration because it's not really that helpful. And so that means the integrating factor, that we care about, that's mu of t, that's going to be equal to e to the power natural log is just, those things cancel, those operators cancel, and so we wind up with the absolute value of t. And so that would be the integrating factor. And in mathematics, when you run into the integrating factor or anything like this with the absolute value of t, so we can just get to this point and say we're just going to use t. And the reason for that is we can treat t as a positive. In most cases, when you're talking about differential equations, time is the independent variable, and so we can talk about positive values of t. So we'll come back to this, but I just want to identify what we've done here. We did step 1. Let me use my blue here. So we did step 1. And then step 2, we computed the integrating factor. Step 2, not 21, step 2. And we could go on and do steps 3, 4, and 5. But I just want to show you what the integrating factor is for the other one. So if we do step 1 for this other example over here, we just have to manipulate. But in this case, notice the actual equation is in terms of some different variables. So the independent variable here is s, the dependent variable is a, so I'm going to rewrite this as dA over ds minus s squared a equals 4. And so I can manipulate this. I can recognize right out of the gate that my g of t is this guy right here. There's g of t, or in this case, g of s. And so my integrating factor, mu, in this case of s, is going to be e to the integral, the g, which in this case is negative s squared ds. And so I just have to do a little bit of calc. It's basically calc 1, and I have e to the power negative 1/3 s squared. Oh, sorry, it's already s squared. It's s cubed. Duh, I'm looking at it. And so this becomes, after I do the exponentiation, there's really nothing that I can classify, or I can cancel here. There's no operators that I can cancel. So this really is, that's my integrating factor. And that's what I would multiply through. So you can see in the first case, just multiplying by t is pretty simple. Multiplying through by this is going to get a little bit more complicated. So just because you can you can figure out what the integrating factor is, it's no guarantee that it's going to make the problem simple. But the nice thing about the integrating factor method is, if you can find the integrating factor, it's a guarantee to work. So we'll stop here, and then we'll take a look in another video at some particular examples.